Welcome back to the Deep Dive. Today we're diving into some really cool research from NVIDIA, all about shrinking those massive AI models we've been hearing so much about lately, those large language models.
LLMs, that's right.
Exactly.
These things are the brains behind those AI chatbots and text generators that are just exploding in popularity.
Yeah, it seems like every day there's a new one.
Totally. But the problem is their sheer size. They often need tons of computing power and resources, which makes them really expensive to work with.
So not exactly accessible to everyone.
Exactly. And that's what makes this paper from NVIDIA so fascinating. It's all about making these LLMs smaller, more accessible without sacrificing performance.
Compressed LLM, kind of like squeezing all the juice out of a giant fruit into a tiny bottle.
Yeah, that's a great analogy.
I love it. So how do they actually pull this off? Where do you even start shrinking something as complex as an LLM?
Well, they focus on two main techniques, pruning and distillation.
Pruning, like trimming a bonsai tree.
Exactly. Imagine an LLM as this vast network of connections. Pruning is all about strategically removing the less important connections to make it leaner and more efficient.
So it's about identifying the dead wood in the model and getting rid of it.
Exactly. And then there's distillation, where a larger pre-trained teacher model guides a smaller pruned student model.
Like a master chef sharing their secret recipe with a promising apprentice.
Exactly. The teacher LLM helps the student learn and perform better, even though it's smaller.
I love that analogy. But there's a catch, right? The training data for these massive teacher models is often kept under wraps. It's a secret.
Yeah, you're right. And that was a big challenge for the researchers.
Because they couldn't just use the original training data for the smaller models.
Right. So they came up with a clever solution called a teacher correction phase.
Oh, tell me more about this.
So before they even start the distillation process, they actually fine-tune the teacher model on a new publicly available dataset. This makes sure the teacher has the relevant knowledge to pass on to the student.
So it's like giving the teacher a crash course in the new material before they start tutoring. I love it.
And what's even more fascinating is they found out that you can actually do this teacher correction thing at the same time as the distillation process.
Wow, talk about efficiency.
It's pretty amazing.
But let's go back to pruning for a second. Are there different ways to actually prune an LLM?
Yeah, there are. And this paper explores two main strategies, depth pruning and width pruning. Think back to that LLM tree analogy.
Okay.
Depth pruning is like removing entire branches, while width pruning is more like trimming leaves off the branches.
So depth pruning is a lot more drastic, like removing entire sections of the model. What about width pruning? How does that work?
So width pruning is all about reducing the number of connections within each layer of the model, streamlining the flow of information within the LLM.
Got it. So they've got these two pruning strategies, this clever way to prep the teacher model, and then the distillation process to transfer the knowledge. What happens next? Did they actually put this to the test?
They did. The researchers actually applied their techniques to two existing LLMs, Mistral NeMo and Llama, and the results were really impressive.
I'm on the edge of my seat. Tell me more. How did these compressed LLMs actually perform?
Well, let's start with Mistral NeMo. They shrunk it from 12 billion parameters down to 8 billion, creating something they call Minitron. And get this, Minitron actually outperformed other similar-sized models on standard benchmarks.
Hold on. It's smaller, more efficient, and it performs better. That's incredible.
And it gets better. For the Llama model, they went even smaller, creating versions with just 4 billion parameters.
Wow, that's a huge reduction in size. Did they use both pruning strategies for Llama?
Yep, they did. They created both width-pruned and depth-pruned versions, and both of them did really well compared to the original Llama model, but the width-pruned version consistently came out on top.
So it seems like carefully trimming those connections within the layers was the key to success with Llama.
That's what it seems like. And there's another really cool thing. The smaller Llama models ran significantly faster, up to 2.7 times faster on certain tasks.
So we're talking about speed and efficiency gains on top of everything else. This is starting to sound like the holy grail of LLM development.
It's pretty exciting research, and here's another really interesting result. In some cases, those smaller Minitron models actually surpassed the larger models they were based on.
Wait, they perform better than their teachers. That's like a student outperforming the master. How is that even possible?
It's a fascinating finding that really challenges our assumptions about model size and performance. It suggests that maybe bigger isn't always better.
Maybe by streamlining and compressing these models, we're actually unlocking some hidden potential and efficiency.
That's one way to look at it. This research really opens up some really intriguing questions about the nature of intelligence and how these models learn. But before we get too deep into that, let's take a closer look at how they actually achieved these impressive results. Welcome back to the Deep Dive. Before the break, we were talking about how researchers are shrinking those massive large language models without sacrificing performance.
And those amazing results, smaller models performing as well as or even better than the larger models they were based on.
Right. And we left off on how they actually did it, so let's unpack some of those techniques, starting with that intriguing teacher correction phase.
Yeah, remember the researchers couldn't use the original training data for those massive teacher models because it's often proprietary.
Right.
So how did they equip the teacher to actually guide the student effectively?
Well, they did this really interesting thing called continued pre-training.
Okay.
Essentially taking that already trained teacher model and giving it kind of a refresher course on a new massive data set called Minitron-4.
So they're basically updating the teacher's knowledge base before the tutoring begins.
Precisely.
I like it.
And this Minitron-4 dataset is huge, about 15 trillion tokens, and it covers a really wide range of topics. And what's remarkable is they only needed to fine-tune the teacher for a relatively short time.
It's incredible how they can make the teacher an expert in this new data set without starting from scratch.
Yeah,
So this correction process was absolutely crucial for the distillation process to work.
absolutely. Without it, the student models wouldn't have learned as effectively.
Okay, that makes sense. Now let's talk about the pruning process itself. I'm curious about how they decided which parts of the model to trim away.
So they used this method called activation-based importance estimation, essentially analyzing which parts of the model were most active when processing information from that Minitron-4 dataset.
Got it. So the more active a part of the model, the more important it must be.
Exactly. And they looked at various components of the model, from the attention heads to individual neurons to the embedding channels, which is basically how the model represents words and concepts.
So they're trying to figure out which parts of the model are really firing up when it's thinking.
Exactly. And based on this activity, they created a ranking of the model's components from most to least important.
Got it. So now they've got their list of what to trim. And we talked about two types of pruning, depth pruning and width pruning.
Right.
Can you remind us again what those are?
Sure. So width pruning focuses on shrinking the number of connections within each layer of the model, like those neurons and embedding channels we just talked about.
Okay.
It's like streamlining the information flow.
And what about depth pruning?
Right. That one's where they remove entire layers.
A bit more drastic.
Yeah, a bit more drastic. And they specifically focused on removing layers that were next to each other because they found that actually produced better results than just removing layers based on their individual importance.
Interesting. So they're not just randomly chopping off layers, they're being very strategic about it. How do they know which layers are safe to remove without messing everything up?
They evaluate those pruned models on a benchmark called Winigrande, which tests the model's common sense reasoning abilities.
Ah, so if removing a layer makes the model worse at Winigrande, they know they shouldn't remove it.
Exactly. It's all about finding that balance between shrinking the model and preserving its performance.
Okay, so they prepped the teacher, they've strategically pruned the student model. Now it's time for the actual distillation process, right?
Exactly. And this is where it gets really interesting. The teacher model actually guides the student by sharing its knowledge, about language, relationships between words and concepts, and how to generate text.
So it's not just about giving the student the right answers, it's about teaching them how to think.
You got it.
Okay.
The student model learns to mimic the teacher's thought process, not just its final output.
It's amazing how they're transferring the essence of the teacher's intelligence to this smaller model.
Yeah, and this knowledge transfer actually happens through something called logits.
Logits, okay.
And these logits actually represent the model's reasoning before it gives a final answer.
Interesting. So the student gets to see the teacher's thought process unfold, not just the conclusion.
Exactly. And this is what makes distillation so powerful. It's not just about shrinking. It's about actually transferring that intelligence from the larger model to the smaller one.
So they're essentially creating a more compact, efficient version of the teacher without losing the essential smarts. Okay, I'm ready to hear about these results. Did this approach actually work?
It did. Let's start with the Mistral NeMo. Remember, they compressed it down to a model with 8 billion parameters, called Minitron.
Right, and it actually outperformed other similar-sized models on standard benchmarks.
It did, and it did all that while being trained on 40 times fewer data points. They tested Minitron on all sorts of tasks, common sense reasoning, question answering, even summarization, and it held its own across the board.
So shrinking it didn't dumb it down at all. If anything, it refined its intelligence.
Yeah, that's one of the key takeaways here. It really challenges our assumptions about size and intelligence when it comes to these models.
Now, what about those even smaller Llama models? The ones with just 4 billion parameters?
They also achieved really remarkable results. Remember, we talked about how they created both width-pruned and depth-pruned versions?
Right.
And both performed exceptionally well. But the width-pruned version was consistently the top performer.
So strategically training those connections within the model layers was the way to go with Llama. And you mentioned earlier that these smaller models were also significantly faster.
Yeah, up to 2.7 times faster on certain tasks. Imagine the possibilities for real-world applications if we can have power and speed.
This is truly groundbreaking research, but I have to say the most shocking result, to me at least, was that some of those smaller models actually outperformed the larger models they were based on.
Yeah, it's a fascinating finding. In some cases, Minitron actually surpassed its teacher model on certain tasks.
It really does challenge everything we thought we knew about model size and intelligence. It's like saying a smaller, more focused brain can sometimes outperform a larger, more complex one.
It's a really profound observation, and it really opens up a whole new world of possibilities for AI development, and it leads to some really exciting questions about the nature of learning and intelligence itself.
This research really has me thinking about the future of AI in a whole new light. Welcome back to the Deep Dive. We've been exploring how researchers are shrinking those massive large language models.
And we've seen some pretty amazing results, those smaller models sometimes performing even better than the giants they were based on.
Truly groundbreaking stuff, but let's shift gears for a minute and talk about the bigger picture.
Okay.
What are the implications of this research? Where does it lead us?
Well, one of the most exciting things is accessibility.
Okay?
Smaller, more efficient LLMs could really democratize AI development, make it possible for researchers and developers with more limited resources to get involved.
So we don't need a supercomputer just to experiment with AI.
Exactly. Imagine a world where powerful LLMs can run on everyday devices, laptops, smartphones.
That opens up so many possibilities. What kind of applications do you see for these smaller, more nimble LLMs?
Well, the potential is huge. Think personalized learning apps that adapt to each student's needs, offering real-time feedback and guidance.
Like having a personal tutor powered by AI and available to anyone with a phone.
Exactly. And think about advancements in virtual assistants. We could have truly intelligent assistants that understand nuance, context, even emotions.
No more frustrating conversations with chatbots that just don't get it.
Right. And let's not forget research. Imagine scientists and researchers in all sorts of fields having access to powerful AI tools that can analyze huge data sets, identify patterns, and accelerate scientific discovery.
All of this powered by models compact and efficient enough to run on their personal devices. It's mind-blowing.
It is.
And it's not just about the applications themselves. This research really makes us rethink our fundamental understanding of intelligence and learning.
You know that idea of smaller models sometimes outperforming larger ones?
Yeah,
Really makes you think.
it does.
It suggests that our current large models may be unnecessarily complex, maybe even bloated.
Maybe we've been approaching AI development with a bigger is better mentality, when in reality a more streamlined approach could actually lead to more efficiency and even better performance.
Yeah, it's an interesting thought, isn't it? It highlights the need for more exploration, more experimentation in the field. We need to push those boundaries.
Challenge the status quo.
Exactly.
This research is a really powerful reminder that innovation often comes from thinking differently.
It really does. And what's most exciting is we're really just at the beginning of this whole journey. The field of AI is evolving so rapidly, and with every breakthrough, we're unlocking these new possibilities and this deeper understanding of intelligence itself.
This deep dive has really opened my eyes to the potential of these smaller, more efficient LLMs. It's a future full of incredible opportunities and some really profound implications.
It is. It's a future that we're shaping right now with each experiment, with each innovation, and with every effort to push those boundaries of what AI can achieve.
And on that note, we'll leave you to ponder the future of AI and the incredible possibilities ahead. Thank you for joining us on the Deep Dive. 766.